Hello, we're going to talk about entropy and enthalpy. Entropy is the system state of disorder. So, for example, if a clean room gets messy, then it has an increase in disorder because entropy is the amount of disorder, not the amount of order. But if dirty room gets clean, then it has a decrease in disorder. Remember that. So S equals entropy, and triangle S, which is delta S, and if you see the triangle or the delta sign, U, that means there's a change in blank, whatever you need to use. That's just for future references. And it's a change in entropy. And a plus change in entropy is an increase in entropy. And a minus change in entropy is a decrease in entropy. Plus, increase, minus, decrease. When climbing up the states of matter, solid, liquid, and gas, it increases in entropy. For example, when a solid turns to a liquid, it increases in entropy. However, if a solid increases to a gas, then it has more entropy than a solid turning into a liquid. As you can see in here, over here in the diagram, the solid, which is the far left, it is very compacted. So there's not a lot of disorder because they have a lot of order because they're very structured. Like, hey, you stay in this row, I stay in this row. It's very, structured. And then liquid is a little bit less loose than solid, but it's not as freely as gas. You can see gas is all over the place going, just all over the place. So it has a lot of entropy, a lot of disorder because it's all over the place. Okay, and the first example, is a decrease because a solid and a liquid goes to a solid. So remember, it's going down. It's going down the states of matter. So remember, solid is very orderly. So that has to be a decrease in entropy because solid is very less entropy. The next one is an increase because it's a solid and then it's going to a solid and a liquid. Remember, a liquid is more entropy than a solid, so it's going to be a lot of more entropy. And then the next problem, there are two, as you can see in my finger, there are 2 grams over here, and so it turns into 1 when the reaction is over. So that means that there's a decrease because they were 2 and now all of a sudden there's 1. So there's a decrease. This is just basically a little bit more, this is just another bullet about the last example we just saw, but here's another example also. It increases when a number of molecules increases during the reaction. So in this example, it's the opposite actually, because in the other example there were 2 grams in the reaction and there was 1 gram in the product, but this is 1 gram in the reactant and 2 in the product. So this is why this is increasing because it went from 1 gas, to 2 gases. And it also increases with entropy also increases with an increase in temperature. Now we're going to talk about spontaneity, or spontaneous process, and non-spontaneous process. The definition is one that proceeds on its own without outside assistance. So, example, if you're going downhill on a bike, for saying, you do not need energy to perform the action because that's the outside force. The outside force is what's pushing you down, so that's spontaneous. But if you're going uphill, if you stop putting energy in, you're not going to go up the hill because you need energy to go up. So if you don't use energy, if you stop putting in energy, you're going to stop the process, and the process will make you fall off your bike and fall down the hill. So that's not spontaneous. Processes that are spontaneous in one direction are non-spontaneous in the other direction. As you can see, when you ride down the hill, that's spontaneous, but if you ride up the hill, that's non-spontaneous. That's the reverse react. Spontaneity. Temperature and pressure are important factors to determine this process. That's going back to like entropy a little bit, because if you're please scratch that out. Temperature and pressure are important factors to determine its process. When ice melts above 0 degrees, it melts spontaneously. spontaneously. However, when the liquid water turns back into ice, it is not spontaneously. If the temperature is below 0 degrees, then it will be the reverse. Basically, this is saying that you have a block of ice, and it's, say, in the area that it's in, whatever, it is 2 degrees. It's gonna melt because it's too high, it's too hot. So that's spontaneous. Just like the person riding on the bicycle, is spontaneous. But now that the liquid is water, now that the ice is water, turning it back into ice is not spontaneous because the temperature is still above 0 degrees. So you really kind of that's really not spontaneous at all. So, but if it was below 0 degrees now, then that will work, because if it's below, then ice turning into water would be non-spontaneous because it's too cold. Enthalpy. Now we're going to talk about enthalpy. It's the measure of the heat gained or lost by the system under constant pressure. H equals enthalpy, and remember this triangle, delta H, change, enthalpy change. And enthalpy change, if enthalpy change is greater than 0, then the reaction is endothermic. And if the change of enthalpy is less than 0, then the reaction is exothermic. We will discuss this in the next slide, what endothermic and exothermic is. Exothermic is the system that is when the system loses heat in the process, and endothermic is when the system absorbs heat in the process. So if a system, so basically it's basically self-explanatory. Look at the example. You see the reactant in the product, and then you'll see the change of enthalpy. Remember, triangle H, or delta H, is change in enthalpy, and it's negative 483.6 kilojoules. The system is losing heat due to the negative sign, as you see in over there, right there. Since it's a negative sign, you know this reaction is going to be an exothermic reaction because it's losing heat in the process. Since the change of enthalpy equals H final minus H initial, the change in enthalpy is the heat of the product, subtract the heat of the reactants. And that's just how it looks like if you see it on worksheets or assignments. It is not the final change of products alone or the reactions alone. So when you do this, you're not going to just find the change. You're not just going to find, oh, what's the change of the, sorry, let me rephrase this better. When you use this formula, it is not to find just the final change of the product alone, or just to find the final change of the reaction alone. It is to find the change of the whole reaction. Not the reactant, but the reaction. And that's basically it for my discussion on enthalpy and entropy. I hope you learned something. Thank you.